Hello, everyone, and welcome to another iBwave webinar. Today, our topic is in-building network evolution from 4G to 5G. It's presented by our Research Director, Vladan Jevremovic, and we will get started in just a few seconds. First of all, I would like to go over a few housekeeping items as usual. You will receive a video recording of the webinar shortly after the webinar. And during the webinar, if you have any questions, please go to the questions box and type them in. Also, in the middle of the webinar, we will have one poll question, and I will put in the link where you can go on your browser to vote when the question appears. It will also be on the slide when you see the poll question. And now I will hand it over to Vladan to get us started.
Thank you very much, Amna. Hello, everybody. My name is Vladan Jevremovic, and these are the topics that I will cover today at this webinar. We will talk about 5G spectrum bands. We will talk about millimeter wave propagation characteristics, massive MIMO and beamforming, in-building network transition to 5G, and network densification. So let's get started. First, we talk about 5G spectrum bands. For 5G network frequency operation, we have two distinct bands. The first one is sub-6 GHz coverage, and that basically covers from 1 to 3 and 3 to 6 GHz. Why am I splitting it into two? Because we have seen thus far 2G, 3G, and 4G networks deployed in bands that are below 3 GHz, and now we have mid-span band, which is 3 to 6 GHz, and we predict that we will see plenty of 5G, fifth generation network action in those bands. Those bands will be used for macro coverage, which is for cellular mobile support, and for umbrella coverage for all macro and in-building venues. What it means is that if I'm betting on ubiquitous coverage, then these are the frequencies that will be at, and mobility will be supported at those frequency bands. Then there is millimeter wave frequencies, and those frequencies are between 24 and 90 gigahertz. That's for fixed band broadband only, and this will be opportunistic deployment. What it really means is that for macro networks, this will be strict line of sight condition between base station and the UE, or this time actually that will be customer premise equipment, because this actually has to be mounted outside of the house or of a building. For in-building deployment, venues with line of sight or near line of sight conditions will be candidates, such as stadiums and convention centers. And then there will be hotspots, such as coffee shop, lunch cafeteria, and conference room. So there will be, for in-building case, there will be, for in-building networks, there will be case studies where we can actually use millimeter wave frequencies. And that is a good thing, because those millimeter wave frequencies allow us things to do that we otherwise couldn't do at lower frequencies. But we will get to that in a second. So for now, we are just need to point out that there are two distinct frequency bands. One will be used as a macro coverage, umbrella coverage, will have mobility, and the other one will be opportunistic deployment in the areas where there is a large congregation of customers, and predominantly line of sight, but no mobility support. So what is the market status for 5G millimeter wave bands? Well, there is plenty of 5G millimeter wave trials, and most of them are between 28 and 39 gigahertz, and most of them are in North America. There are some in APAC region, and but there are also a portion of very high frequency, which is above 60 gigahertz, that is being trialed. So what we expect is the first deployment to be in North America in the second half of 2018. And we expect that to be in the range between 24 and 39 gigahertz. The range will be limited. It will be outdoors mostly, and it will be limited due to the high propagation loss and a high penetration loss. There is another thing that is not explicitly written here, but for those of you that have dealt with deployment in 24 to 39 gigahertz about 20 years ago, you may remember that there is a third component to it, which is the loss due to the heavy rain. And those frequencies are susceptible to high loss during heavy rain. So in various portions of the world, the rain may vary from a mist, which is in Pacific Northwestern United States, specifically Seattle region, to very heavy torrent rain, which is the type that you see in, let's say, Florida, in Miami area, or in parts of Texas. So that is something that needs to be taken into account if you are designing macro networks at those frequencies. But we are dealing with indoor, so that's obviously is not something that we are concerned about. So as we have said, indoor use cases likely targeting hotspots and other venues, and some venues that is predominantly line of sight propagation. Now back to you, Amna.
Okay, let's go to some questions that were submitted when people registered for the webinar. So the first question, Vladan, is why are millimeter wave bands considered for 5G?
That's an excellent question, and we have known about millimeter waves for a long time now, and we know that there were problems with propagation, and it can propagate through foliage, and it is not good for a blanket coverage in a market. So why are we looking into it now? The reason is that despite of all that, those are very wide RF channels that those frequencies carry. Simply, the higher you go in a frequency, the wider RF channel you're going to have. So at 24 gigahertz and 24 to 39, to be precise, those channels are 850 megahertz. So because you have such a wide channel, you can carry a lot of information over that channel. For your 64 QAM, for example, it can go up to 6 bits per second per hertz. Obviously, it's going to be a little bit less than that, but when you multiply 6 by 850, you see how high data rate you can get even with a 64 QAM, not 256. It will go even higher. So that's the reason why we are seeing it now. This is a second go at this band. The first one 20 years ago ended in bankruptcy of the license holders, but we are hopeful that now, as a part of 5G, this band will be resurrected and will have a much brighter future. Amna?
Okay, so the next question is, will we see smartphones with millimeter wave chips, and when?
So Qualcomm has just announced, I would say, a week ago, that they made a millimeter wave chip with a very small form factor, and that chip can actually fit in a smartphone. And then, so obviously, that is a good news. And they also had that they're hoping that this chip will find its way to a mass market within about 9 months, I think. I think that was how they worded it. So obviously, large chip manufacturers are working on it. Qualcomm has just announced that breakthrough, and so we are hopeful that we will see smartphones with millimeter wave chips in the first half of the next year. Back to you, Anna.
Thank you. See if we have another question, or we can go to the next topic.
Okay, so millimeter wave propagation characteristics. So what is so unique about those bands that we don't have at the lower frequencies? The first is material penetration reflection loss that needs to be characterized. It's different than what we are seeing at sub 3 gigahertz bands, even sub 6 gigahertz bands. And to calculate the penetration reflection loss, We need to know material thickness, and we need to know material's complex electrical permittivity. This complex electrical permittivity is important. It's not enough that you know just the absolute value. You need to know the full complex electrical permittivity expression for that particular frequency. So then the best way to approach this is either you go ahead, you go out and measure those yourself, and then you publish a paper, or you just go in and look into what has been published thus far. And I'm now listing the materials with published permittivity values in the frequency range of interest. This first row that has concrete, plasterboard, glass, ceiling board, chipboard, and metal has been published in the range from 1 to 100 gigahertz. Cement block is in the range that we are interested, 28 to 38. So those listed, 1 to 100 and 28 to 38 is what we are looking for. Wood is a little bit off. It is at 42 gigahertz. And then there is a whole slew of materials listed that has been characterized at 60 gigahertz and maybe a little bit above. So our challenge is to find a more comprehensive list of materials that have been characterized at 24 to 39 gigahertz. Obviously, 60 and above is nice to have, but it looks as of right now that this will be a secondary millimeter wave frequency band for exploring 5G deployment. And there is a good reason for that. 24 to 39 gigahertz is a licensed band, and operators love their licensed bands. They would just rather buy a company that used to own, that actually owns those frequencies, or go on an auction and get those frequencies themselves, than to just deploy something in unlicensed band. So that is, the problem that we have right now. We don't have that many materials, but we are hoping that in the future that may change. So what else is out there? It's diffuse scattering. Now, what is diffuse scattering? Diffuse scattering is basically when your signal hits the wall and then scatters in all possible directions. And why does it scatter? It scatters because there is something called surface roughness that makes the signal basically go in all possible directions. And then the question is, why is there surface roughness at millimeter wave frequencies, and there isn't any being taken into account in, let's say, sub 6 gigahertz? Well, the reason being is that it's the same wall, right? But it just seems to be rough. It looks to an incoming wave as a rough surface if the incoming wave frequency of operation is high enough. So what does that mean? Well, it means that whatever roughness on the surface has to be comparable to the size of the wavelength. What does it mean? Maybe a quarter of the wavelength, maybe a fifth of the wavelength, maybe a tenth of the wavelength. That is, how we define a surface roughness. But then we have to figure out what it really means in practical terms. If I have a wave that operates at 1 gigahertz, then my wavelength is 30 centimeters. If I have it incoming wave at 30 gigahertz, then the wavelength is only 1 centimeter. So let's say that I have a surface roughness that is of the order of the quarter of a centimeter, which is really small. It means that that surface roughness, which is quarter of the centimeter, when I compare that to the wavelength of the wave at 30 gigahertz, which is only 1 centimeter, it seems, I would say, big enough. It is comparable. It is quarter wavelength to a full wavelength, right? So it is, I cannot just say, hey, it's a small surface roughness, because it is comparable to the wavelength. On the other hand, if the wavelength is 30 centimeters, which is when your incoming wave is at 1 gigahertz, then quarter of a centimeter doesn't seem like something that can concern that wave. It is very small compared to that wavelength. So that's why we consider that wall flat for those frequencies. So that is the difference between the wall at 1 gigahertz and the wall at 30 gigahertz. The 30 gigahertz wall may look like a rough surface, even though it is the same wall as if the incoming wave is at 1 gigahertz. So what else is out there? Well, when we talk about diffuse scattering, then there are three types of diffuse scattering, which even complicates things some more. The first one is Lambertian scattering, when you have a signal that is going to disperse in all possible directions indiscriminately when it hits a rough surface. The second one is directive scattering, which you would intuitively think that is something that you would expect. Most of the signal is going to the direction of the reflection, and then some scattering around is to be expected. Then the last one is the one that is, to me at least, the most peculiar one. I have an incoming signal, and it reflects and takes most of the power with it. There is some scattering, but then there is some back scattering that goes in the opposite direction of the reflection of the incoming signal. So this is another challenge for us, to model those three types of scattering for all in-building materials, for all millimeter wave frequencies of interest. So there you have it. First, we need to figure out what is electrical permittivity at millimeter wave frequencies, and we don't really have all that many reference materials to begin with, especially for the frequency band between 24 and 39, which seems to be the first on the block to get deployed. And then we need to figure out whether a particular material is going to conform to Lambertian scattering, directive scattering, or the third one, and then we need to figure out what the parameters, each one of those has its own parameters, should be. So quite a bit of work for us at iBwave. Amna, back to you.
Okay, let's go to a question. So why are there more material characterized at 60 to 71 gigahertz than at 24 to 38 gigahertz?
It's an excellent question. It is basically because that above 60 gigahertz is unlicensed spectrum, which was slated for deployment of 802.11ad. This is a standard that has been completed, I would say, a couple of years back, and the work on that standard started, I would say, about 5 years ago, maybe 6. And then, so what that means is that, those transmitters and receivers were available back then, and then academia got hold of those, and because it was unlicensed band, they could do experiments there, and quite a few papers have been published on the account of a research that will be relevant to 802.11ad. Now, that's the reason why we have so many papers at above 60 gigahertz. As for 24 to 38, I kind of hinted that that was a hot topic about 20 years ago, and then as soon as they figured out that there will be no propagation through external walls because they're thick and heavy, like brick walls and reinforced concrete, then the motivation to go ahead and explore other materials diminished. And those transmitters and receivers, they were not plentiful because that was a pretty much dormant industry, that fixed broadband wireless at millimeter wave frequencies for about 20 years. So, and also it was a licensed spectrum, so having experiments in licensed spectrum is always a little bit dicey, So anyway, now there is a renewed interest, and we are hoping to see more papers to be published going forward, especially in the light of the fact that now, whoever is doing experiments is figuring out that some materials may actually be porous to millimeter wave frequencies, but that's something that we will address a little bit later. Amna, go ahead.
So another question is, can a millimeter wave signal pass through walls?
Yes, so we looked into published values for some of those listed materials, and we found out that at some frequency bands you actually may see some millimeter wave signals going through some materials. What it means is that, like I said, reinforced concrete, brick walls, you will not see the signal pass through, because typically those are 20 dB or higher penetration loss. But for, let's say, plaster, you would see the signal that actually can pass through. You will see maybe 7 dB loss or so, which means that you will get through the first wall. Okay, so what it really means is that for some interior materials inside a house, for example, like plaster wall, the signal can get through that first wall. So it is not complete line of sight propagation. Some materials can be penetrated at millimeter wave frequencies. Hamna?
Okay, so what are the typical penetration loss values at millimeter wave frequencies?
So yes, I just answered that question. We can see several dBs for light materials, interior materials, and then we see on the order of tens of dBs for exterior house, exterior building materials. All right, so those are the questions that we had. So I'm going to move on to massive MIMO and beamforming. So for massive MIMO, what does it mean? It means many antennas, plenty of antennas at base station, up to 128. And then you will see something that you maybe have not been used to as for the nomenclature, like 64 by 64 by 2. So what does it mean? You will have 64 transmit antennas and 64 receive antennas, and that will be your 64 MIMO. But you're also going to have antennas that are cross-polarized. One may be vertical, one horizontal, or both of them be cross-polarized. But the point being is that one MIMO location, instead of one antenna, you will have two. So that's why you have 64 by 64 by 2. And that's why I'm telling you it's 128 antennas, not 64 antennas. So in each MIMO location, there is two antennas, and they're linearly polarized, either HV or two cross-pole. And why do we have that? We do that to decorrelate signals. So basically, you can do it in two ways. You can send the same information on both of those signals, on H and V or cross-pole, and then, or you can send half of the information on each one. Regardless, you are using it to be able to decorrelate signals, and also that we have seen that using cross-pole antennas is actually good for decorrelation signals, as good as, let's say, do the spatial separation. And spatial separation is something, that when you are doing the massive MIMO, it's not something that is done with a smile on your face, because it eats up your valuable space. And I'm going to show that in a second. But before that, I'm going to talk about the fact that you need a separate RF connection back to transceiver. So basically 128 antennas, 128 connections back to the transceiver. So how does that look like? Well, it looks like something like this. This is a picture that has been taken at Mobile World Congress in Barcelona, and care has been taken that we remove all the references to who the manufacturer was. And to be honest, I don't even remember who that was. But what you are seeing is, and I'm not quite sure what is the order of this massive MIMO array, but what I would like to point out that what you are seeing is a cross-pole in each location. So this is location number 1 for one transmit and receive antenna, and you see two cross-poles. So this is the first location, second, third, and fourth, I think, and then that is in horizontal direction. In the vertical direction, you have 1, 2, 3, 4, 5. So maybe it's 20 by 20. I'm not quite sure. This picture is not, taken from the front. But the point being is that you see a big panel. Okay, you see a big panel, and this is massive MIMO antenna array, and the space is at premium. Okay, so this looks really big, and shall I say looks expensive from what I can tell. So those are two things that need to be kept in mind when you are thinking about massive MIMO. There is going to be a panel. That panel is going to be fairly big, and there is going to be a bit of a real estate associated with it because it's a big antenna, needs to be placed on the base station, and this is obviously going to be expensive because you have so many antennas, cables, amplifiers, and so on and so forth. So the second thing is beamforming. So what exactly is beamforming? Beamforming means that I'm going to have this massive MIMO array, and then I'm going to, based on that MIMO array, I'm going to form a beam that is going to give each serving UE its own optimized antenna array radiation pattern. And not only that, it is also going to actually minimize the interference for all other UEs that are being served at the same time as the target UE, which means that on the same channel, I can serve multiple UEs, and providing that they are, spaced out enough, they're not right next to each other, then, I can maximize the signal in the direction of the UE that needs to receive that particular signal. And other UEs that are being served at the same time will not hear much of that signal, which means that signal to interference and noise ratio will be very favorable. So this is how it looks like, from the standpoint of illustrating M antenna array that forms K peaks serving K UEs. And not only that they're maximizing this antenna array peak in this direction, it basically minimizes that signal, the same signal, in the direction of all other UEs. So this looks really great on paper. And the question is, how do you model this? So for each base station, what you need to do is specify three things. Number of UEs that are in coverage. You basically would want to know their locations as well, right? Then number of antennas at the base station, that it is that 64 by 64 by 2 that we talked about, or maybe something less than that. And then what is the throughput, megabits per second, that you would like to have on your phone. And then based on that, what you need to do is you need to find the optimum ratio of antennas to concurrent quad channel users to achieve that specified UE throughput. Now, why do you want to know that? Because if you know that the number of concurrent quad channel users, then you can actually calculate not only that specified throughput, well, you know what it is going to be, but you can calculate capacity as well, right? So that is actually the whole art of massive MIMO. It increases the capacity of your base station, but it also helps improve the signal to interference and noise ratio for your phone. And obviously, this is something that is very computing intensive. When I say that, I mean that, the base station has to calculate all those antenna array coefficients in real time and apply that. But also it is going to be computing intensive on our end in RF simulation and planning software. With that, I'm going to turn this back to Amna.
Okay, so as I mentioned, it's time for our poll question. You would see the question on the screen. There is a link, or you could also, if you're in Canada, text with the number given, text iBwave first to join and then your choice. I'm also going to send a text message with the link so you can click and join. Chat message, sorry. And where you can click directly and vote for your choice. So the question is, what is the strategy for deploying massive MIMO? And you have A, B, C, D, and E as your choices. So vote now.
They would say vote early and vote often.
We'll give it a few minutes to make sure we have enough responses. Okay, Vladan, I think we have some results. I see the majority is choosing all of the above.
Okay. All right. So that's the people have spoken, as they say. So let's go back to actually the next break. This is the question. What is the strategy for deploying massive MIMO? So we figured we will let hear the audience before we actually answer this question. We wanted just to see what everybody else thought. What we have seen is two things in the market. The first one is what is being reported of the trials, and massive MIMO has been trialed at both millimeter wave frequencies and a 3.5 gigahertz free band, which is sub-6. So from that point, it will be both millimeter wave and sub-6. Now, indoor and or outdoor or both. We have heard at a couple of conferences that the strategy that operators are considering is actually deploying massive MIMO outdoors only, not indoors. The reason is twofold. The first one is real estate. Those panels are bulky. And the second one is the cost, because the cost of massive MIMO is with the base stations, with all the amplifiers and the antennas, is going to be significant. And well, the third one is kind of mixed with the first one. It's the form factor, right? You can't really put it in a small enough space, confined space enough, like which is what you would expect to see indoor. So indoor massive MIMO, we are not sure about that. We have heard that 4x4 MIMO will initially be deployed indoors, but not massive MIMO. So yes to millimeter wave, yes to sub-6, but no to indoor, and yes to outdoor. So in-building networks transition to 5G. So let's take a look as to what we have today. For passive DAS, we have many remote antennas, and those remote antennas are actually their RF paths, their RF cables are combined in via combiners and splitters in a few stages until all antennas are combined into a single RF coaxial cable that terminates at the indoor base station. So what it means that there is no direct RF path between antennas in a passive DAS and to the base station. There is no dedicated RF link. So what it means is that whoever deployed passive DAS really decided to forego 2x2 MIMO in favor of SISO and the reason being is the cost. Okay, we have seen that being deployed quite a bit that way in Asia and some in Europe, but not really in the US. So now, if you assume that 4x4 MIMO is going to be at least initially deployed in building, then it means that each of those SISO antennas needs to be replaced by 4 MIMO antennas, and each of those 4 antennas has to have its own dedicated path toward the base station. And then so if you can imagine, that's quite a bit of change of philosophy as to what we had prior when we were combining all RF antenna paths into a single cable. Now we have to have dedicated cables from 4x4 MIMO into the base station. So for fiber DAS, we had 2x2 MIMO mode. That was not a problem at all. Remote units were 2x2 MIMO. And now, if you assume that it will be 4x4 MIMO as a strategy, then those need to be upgraded or replaced with 4x4 MIMO remotes. But you really do not need to touch any cables, because there already has been installed a fiber cable to that 2x2 MIMO. And then so you don't need to do anything with regards to that cable. The question is, what happens if you had a 4G small cell network in building? Well, replace 4G unit with a 5G unit. You don't need to add any antennas to it. That presumably that 5G unit indoors will be 4x4 MIMO. So what is the most economic migration option? Well, passive DAS is not really feasible for in-building 5G in-building networks, because there should be a massive investment in the infrastructure, in the DAS infrastructure with antenna arrays and coaxial cables, and cost of labor is not scalable, which is very, very important. On the other hand, small cells and fiber DAS, they are much better migration option, because the cost of labor is scalable and there is no need to replace or upgrade fiber when upgrading fiber DAS to 5G. So the verdict is in. We believe that passive DAS cannot be efficiently migrated to 5G, while the other two types can. Back to you, Amna.
Okay, let's go to another question. How is the transition from sub 3G to 3 gigahertz to 3x6 gigahertz going to affect indoor range? Would I need more antennas?
So the question then is, okay, what is your starting point? So for example, if you want to migrate your 2.1 gigahertz network to 3.5 gigahertz network, you may be okay. You're going from, let's say, 2x2 MIMO to 4x4 MIMO, and you have more MIMO antennas, and that gap is not all that great, so you may be okay. You may survive without having to put more antennas. But if you had a passive DAS at 1.8 gigahertz, for example, and you want to migrate to 4.9 gigahertz, which is the case in China, then you may need, a whole new network with more antennas. So it all really depends on what is the starting point and what is the end point. And in most of the world, there are regulatory bodies that will tell you this is the frequency at which you must deploy the new generation of the networks. And that's a good and bad at the same time. Good thing is, because this is really a spectrum where there is nothing as of the moment of the spectrum bidding, so you can deploy at your own leisure. The bad thing, and that is actually good, because you do not have to refarm the spectrum. There is no existing 4G traffic there, so you can go and experiment and then deploy 5G. Bad thing is, sometimes you're given a spectrum that is not favorable for various reasons, and which is what happened in China when they gave 3.5 and 4.9 gigahertz, and the operators operate between 1.8 and 2.3 gigahertz. So the ones that actually got 4.9 had to migrate for 1.8. That is almost 3 times. And if you look into how many dBs it's there, it's probably about 9 or 10 dB difference. So in some countries, like in China, there will be problems when migrating from indoor net or from 4G to 5G indoor networks. And in some, maybe less so. So, don't think we have any more questions in that break. Yep. So I'm going to move on to network densification. So network densification is something that should be by now a very well known process, which is a process to which we are placing actually radiating elements close to where people are, which means indoor DAS, outdoor DAS, Wi-Fi APs, small cells, etc., in convention centers, in stadiums, in hotels, at airports, putting radiating elements closer and closer where the customers are. And as you put them closer to customers, you actually give them less power to transmit, and the coverage is smaller and smaller. So that gave rise to the term HETNET, or heterogeneous network, to signify the fact that there are radiating elements that are different in terms of transmit power, in terms of the coverage scope, and in terms of the form factor. So we call that HETNET. So the future is the crystal ball owned by Cisco tells us that the cellular data growth will be 7 times between 2016 to 2021. Now, not sure why Cisco would do a research on cellular data, but I thank them for that because it makes my job easier. And I can tell you that there is the growth of cellular data is going to be unimpeded from the year 2016 to 2021. And most of it will be in APAC region, but North America and Western Europe will get their fair share. So what does that really mean for all of us? Means that most of this traffic will originate indoors, right? So we're going to see more indoor traffic, more cellular data indoor traffic. So what is the impact on in-building? What does it mean? Why am I talking about this? Well, look at it this way. Your number of in-building projects are likely going to increase by an order of magnitude. Let's say in the near future, you're probably going to see 10 times more of in-building projects, because most of the traffic, the increase in traffic, will happen indoors. Well, yes, you are going to deal with it efficiently in terms of putting a new technology, which is a 5G, or maybe even getting a larger pipe, but which is millimeter waves. But chances are you will get more in-building projects, if not by a factor of 10, maybe by a factor of 5. And this is going to happen within the next 5 years. All right, so far so good. Now, the truth is that some of those projects that are completed, they will fail out of the gate. What does it mean? Unacceptable quality of experience for customers, right? So it happens. It doesn't happen often, hopefully, but it happens. So the rate at which those projects fail, we call project failure rate. So let's say that you have 10 in-building projects in a year, and typically 1 or 2 are going to fail. Okay, let's say just 1. That's 10%. So your project failure rate is 10%. All right, so you have maybe one guy that's doing your in-building projects, and one project fails in a year. It's not a big deal. He's going to handle that. But what happens if the number of projects over 5 years increase 10 times? So now I still have that one guy, and he has to deal with 100 projects. Okay, well, if they keep on coming with no problem, if it is only still one project that fails every year, he's going to be okay, hopefully. But what if it is still failure rate at 10%? It means that 10 projects is the number of failed projects right out of the gate. Now he cannot deal with all those. You have 100 projects that are coming his way every year, and then 10 of them fails. So you're going to need to hire more people. Now, you can do that, or you can do something else to avoid project failures, and that is to standardize your RF design and planning process and standardize your RF design tools. Okay, now if you do that, then hopefully, you know, recovery of those projects is going to take a shorter time, and also you're going to catch the errors before they actually go live. So to that end, I'm going to give you a nice case study of a large-scale deployment in India. Then the challenge was there were 17,000 small cells to design in 2 years with a team of 100 engineers. So that's really a tall task. And then we were faced with the issue of how to complete everything on schedule, how to best use the resources, and how to store the info for future access. So we gave them the solution for survey design and operation and maintenance. For the survey, we gave them iBwave Mobile, which was capable of digitizing notes, pictures, and drawings into iBwave file, integrate RF data into iBwave file, and create preliminary design on-site and upload to cloud being iBwave Unity. From iBwave Unity, you can use iBwave Design to download the file, create final detailed design, and that give all the appropriate screenshots of your KPIs, appropriate coverage maps. And those are used to create key reports. And then everything is stored in iBwave Unity, which is not just a depository, but you can also use that to do a search of projects. For example, you can find all projects that are greater than 100,000 square feet, or all the projects that were done using, let's say, a particular equipment, and sort them out. And actually, you can figure out, you know, certain similarities between projects. And you can also use this to create key reports. The point being is that those three were standardized across the board, as well as the best practices. And then in the end, there was a comparison between what is going on when you have a streamlined process with those three products of iBwave versus traditional process where you would use, let's say, Excel spreadsheet, for example. So either one design every 3 days per designer with a streamlined process, or one design every 2 weeks when the process is not streamlined, right? So what it really it means is that 65% of designs were completed in just 125 days. And then so that concludes my presentation, and now we are open to questions. Amna, back to you.
Okay, thank you, Vladan. We do have a number of questions here. So there's one here. If millimeter wave is used for IDAS, how can we reuse existing antennas and RF cables?
Right. I would say that you cannot really do that, and it is not used. Millimeter wave will most likely not be used for IDAS. Most likely it will be small cells. And there is one particular product by, I think, Samsung. Samsung actually has made a press announcement about 2 months ago, in late May, that they have actually gotten FCC approval for their in-building small cell at millimeter wave frequencies. So most likely that's what you will have at millimeter wave, not IDAS. I'm thinking IDAS probably may happen at sub 6 gig. At 28 millimeter wave, you will see small cells.
So another question is, will 5G be adopted for indoor, and what is the timeline?
Yes, it will be adopted for indoor. We actually have already seen this one product I just mentioned, Samsung indoor millimeter wave small cell that was announced back in May. If you do a search, you will see that was announced. So we will see that probably at the same time when we hear an announcement that millimeter wave chips are going to be included in the next generation of Samsung or iPhone phones, which, you know, probably is going to happen sometime mid next year. As for iPhone, I don't know what their plans are. I'm just guessing. But from what Qualcomm has announced, that they just announced that chip, and then they said that they think it's going to take another 9 months, for that to be adopted into mass production of smartphones. Then I'm thinking that most likely that's what we are going to see.
Okay, so there's another question. What are the tips to design current solution to prepare for future millimeter wave solutions?
Yeah, we are working on it. We are working on actually putting antenna radiation antennas, millimeter wave antennas into our database, and we are actually this is on our roadmap. Millimeter waves are. I really can't tell you more than that because I'm not PLM director. I'm research director, and I can't really tell you what our plans are for the future. But we are working on this.
So another 5G question. Will 5G be deployed in mid-bands such as 4 gigahertz?
Yes, it will be. 3.5 is the band that actually has the most interest worldwide. And interestingly enough, if you look into what 3GPP is saying about 3GPP approved the frequency bands, you will see that 3.5 has been 3GPP approved band. We have not really seen much deployment in 3.5 for LTE. From what I can tell, there are only a handful of countries where 3.5 gigahertz has been deployed. One of them is Japan, and the other two, I would say there is one in Middle East and there is one in Europe, but I'm not quite sure what they are. So only a handful of countries has used 3.5 thus far, but going forward, we have seen a lot of trials at 3.5 for 5G. So my guess is that 3.5 will be of great interest for 5G worldwide. Now in the US, I'm not quite sure what is going to happen because 3.5 is actually slated for CBRS. Doesn't mean that it won't be deployed there, but it may not be necessarily deployed as a licensed band, but as a managed band, which is a different model.
Okay, thank you, Vladan. So let's do one last question. Is there any interference between millimeter wave signals and the umbrella signal?
No, because that would be the completely separate bands. Umbrella will be at sub 6 gigahertz, and this other will be at 28. So I don't really foresee them interfering with each other.
Okay. There is another interesting question. I think let's make that the last one. Is there any real 5G indoor trial for both 3.5 gigahertz and millimeter wave?
Maybe there is. We are not operators. We only hear, here and there. So we don't know. The answer is whether it is both 3.5 and 28. The answer is I don't know. And even if I knew, I may, have a non-disclosure agreement, which would require me to tell you that I don't know.
All right. So I think that's all the time we have. I had some questions here asking about the presentation and the recording. So as I said, we will share the recording with everyone who attended and registered for the webinar shortly, as well as a link to Vladan's full white paper on the topic to give you some more information. So thank you everyone for attending, and thank you, Vladan, for the informative webinar. I will now end the call.
Thank you, everybody. Goodbye.